Let us go to the next section. That would be energy transfer by heat. Okay, energy can be considered as energy transfer when it crosses the system boundary. Okay, if a kind of energy does not flow in or out of a system, it cannot be said to be a kind of energy transfer. Okay, so what we are considering in the energy transfer should be the energy flowing across the boundary. Okay, the first kind of energy transfer discussed here will be heat. Okay, well, heat is defined as a form of energy transfer from one body to the other that is driven by the temperature difference. Or we say that the driving force of this kind of energy transfer will be temperature difference. Okay? Heat must flow in a direction that it is from a high temperature region to a low temperature region. Okay? So that will be the natural flowing direction. The rate of heat transfer depends on the temperature gradient. Okay? If there's a large temperature difference, then there will be a large rate of heat transfer, and vice versa. Okay? Well, we will have another term called adiabatic process. Okay? We have talked about adiabatic in chapter 1, but we will restate it here because it's about heat transfer. So adiabatic process is a kind of process in which there is no any heat transfer. Okay? But please do not confuse this with isothermal process. That means in the whole process the temperature remains the same. Okay? They are different. Adiabatic process and isothermal process, they are different. Okay? It's because the temperature of a system can also change by using other kinds of energy transfer, for example, work. Okay? Energy transfer by work can also change the temperature of a system during a process. Okay? But there's no any heat transfer. Okay? So they are different. Well, in thermodynamics, we usually express the quantities in per unit mass basis, as I've said in the previous slides. While heat is not an exception, we have a heat transfer per unit mass here. That is Q equal to big Q divided by M. Okay? Small q means unit mass basis, and we will also have kilojoule per kg. Again, it's not the default unit. The default unit should be joule per kg if you use the correct SI units throughout the calculation. Here, Q is the amount of heat transfer. Okay? Well, if the heat transfer rate is varying, then the amount of heat transfer during a process from time 1 to time 2, we need to use integration to determine the amount of heat transfer in this time interval. Okay? So Q equal to integration of Q dot dt in the units of kilojoule. Okay? Well, here, as we know that integration is just a kind of summation while you divide the whole process into infinitely small intervals and you sum them up. And when you add them up, we will get the total amount of heat transfer. Here we will talk about some mechanism of heat transfer. Well, there are 3 mechanisms for heat transfer: conduction, convection, as well as radiation. Okay? Conduction describes heat transfer from a high temperature region to a low temperature region by means of an interaction between the particles. For example, collision of particles, as well as some movements of electrons. Okay? The rate of heat transfer by conduction is given by what we call the Fourier's law of heat conduction. That would be Q dot conduct. Okay? Here COND means conduction equal to negative kTA dt dx. KT is what we call the thermal conductivity, and it has a unit of watts per meter K. Watts per meter K. Okay? So we will also use what we call the thermal conductance, G, to describe the heat transfer rate, which is called G equal to kTA divided by delta X. Okay? We will use this to group the term here. Okay, that means we take the dt away, so that we will have kTA divided by dx. If you think that in an average sense, this d and this d will become the triangle delta. Okay, delta t divided by delta x. So this kTA divided by delta x can be grouped by using a constant called the thermal conductance. Okay, so that the whole expression will be equal to Q conduction equal to G times delta T. Okay, here we have a negative sign here because the heat transfer must flow from a high temperature to a low temperature. So that we'll have a minus here. Okay, another type of heat transfer will be convection. It's a mode of heat transfer which is resulted from the combined effect of a conduction as well as the bulk motion of fluids. Okay, when the fluids are moving, then there will be also convection occurring. The rate of heat transfer by conduction will be given by this expression. Okay, that is here. This is what we call the Newton's law of cooling. So here COMV stands for convection, it will be equal to H times A times the temperature difference, Ts minus Tf, okay? Ts means the surface temperature, while Tf is the temperature of the surroundings, or the temperature that is far from the surface you are concerning, okay? And H here will have a name for that. That will be the convection heat transfer coefficient, okay? And the value of H depends on many factors. For example, the nature of fluid, whether it's a liquid, whether it's a gas, and also whether it's viscous, okay? Whether it's viscous or not, okay? And it also depends on fluid velocity and also surface roughness, okay? Because surface roughness would affect the kind of fluid flow on that surface. As this mode of heat transfer is related to fluid motion, so knowledge of fluid mechanics is inevitable. But at this stage, usually the value of H will be given and one just needs to substitute the corresponding values into the formula for the calculation, okay? At this stage, you don't need to bother about the things in fluid mechanics or the things you need to learn in heat transfer. Well, you just need to use the formula, plugging the corresponding values into it and get the answer, and that will be enough, okay? After that, we will talk about the third type, that is a radiation, okay? Radiation is a kind of heat transfer process which is carried out by the emission of electromagnetic waves or photons, okay? The maximum rate of emission of radiation will be given by the Stefan-Boltzmann law, okay, which is this one. Q emit max dot equal to sigma times A times Ts to the power 4, okay? It is raised to the fourth power of the surface temperature, while the Ts is the absolute temperature of the surface, okay? Remember, it's the absolute temperature. So before calculation, if the problem has given you the Ts in terms of degree C, you need to convert it to Kelvin, okay? But note that this is just a theoretical maximum that is emitted by idealized surface called black body, okay? Well, therefore, this kind of a radiation, we will call that the black body radiation, okay? That is the Q dot emit max, okay? All real surfaces emit less radiation than a black body and the same temperature. And the rate is given by Q emit equal to epsilon sigma A Ts to the power 4. Okay? So here we will have an extra factor epsilon, and this epsilon we will call that the emissivity. Okay? Which ranges from 0 to 1. Okay? And for the net radiation from a real surface, we will have the following formula. That is this one. Q radiation equal to epsilon sigma A times Ts to the power 4 minus T surrounding to the power 4. Okay? So we will have this kind of formula so that we can get the net radiation. Okay? Because for the surrounding, it also have temperature, so it will also emit some radiation that you will absorb. So that the net radiation emitted from the system, then you need to minus the original emission by the absorption. Well, provided that the surface having temperature T surrounding is much larger than the surface at temperature Ts and can fully enclose the surface. Okay? We have some assumptions that the surrounding is very big such that it can fully enclose the surface emitting the radiation. Well, for more details, please refer to the textbook as well as a Mechan 3310, that is a heat transfer, for details. Okay?